Howdy, ST 589, Lecture 14, Fundamentals of Information Technology. This is the second part of Chapter 11. And Chapter 11 deals with information systems development. Last time we talked about the broader overarching job of systems analysis, which leads to an end product of a blueprint to develop the system. And of course, it goes beyond that. But tonight, we're going to talk about the programming portion, which is the implementation phase of the systems development lifecycle, SDLC. And we're not going to go, this lecture isn't going to go into how to program necessarily, just some conceptual things, because none of us really needs to know how to program. But I do want you to have some understanding of what's going on. And we have laid a foundation here. We've talked about the analog reality we live in, and the binary reality the computer exists in. And of course, in order to tell it how to do things, we have to have a methodology, we have to have a process, and that is programming. We create a file of instructions, something we can enter because we are the ones telling it what to do. And of course, we have to have a process to turn that file of instructions from our analog world into the binary world of the computer, or digital anyways. So we're going to take a look at that process at a very high level. Without programming, of course, we wouldn't be using computers. You know, they would just be a doorstop. So the programming is what makes it run. Windows is a program. Word is a program. You communicate via the internet with a program. Your browser, Internet Explorer, or Firefox, Mozilla, is a program. And it has a specific tasks, and it does specific things. It accepts input from you and input from other places, and outputs your input and inputs your output. So the programs are what make it work. It's what interfaces between you and the hardware, if you will, and allows us to store a file of things. So the programming process is a big part of the systems development, and of course it really creates the system. A lot of other things have to happen, but this is an important one. Some of the things we're going to look at, and we may not look at them in very great detail, the different levels of languages. There's a thing called object-oriented programming. And what I've found recently is most of the students I get understand that in my information technology classes for the University of Maryland, understand that process better than they ever have before, because that's what they're being taught now. The old style programming is kind of falling by the wayside, but still exists. We're moving to object-oriented, which allows us to invent something called black boxes that can be used in a lot of different ways without changing a program. And we'll talk a little bit about that. And we're going to take a look at examples of some programs. Programming languages, I meant. We're going to look at web pages a little bit. I'll show you a quick and dirty way to create a web page using Word. Most of you probably know it, but if you don't. And we're going to look at the programming development cycle. Yes, there's a cycle here too, which is very similar to the system development life cycle. Same idea, phases, different steps. And we're going to look at the basic control structures of a program. So you'll have some understanding of how you might approach a program. Computer program is just a list of instructions. Pretty straightforward. By the way, here's a list of all kinds of computer languages over here. So there are levels of languages, and this is generally follows the history of computers. I mean, in the early days, computers were so slow and had almost no RAM that you had, the only thing you could have was a low-level language. And what that means is it only runs on a specific computer. So you would write a program, and the language you used to write that program only worked on that one machine. So essentially, you're very close to the hardware, because every computer a Macintosh has a different instruction set than does an Intel-based, Windows-based system. Okay? So when you get down to the hardware level, the instruction set, the machine language, is specific to each computer. With a low-level language, when you wrote the program, you couldn't run it on another computer because the language was that specific. When we get to higher level languages, it becomes machine independent because of the program that converts it to machine language. And we'll talk more about that in a little bit. And of course, very rarely do people use this anymore, although the computer science department here does require people to learn assembler. And I've written applications in assembler, and it's no fun at all, just so people can understand machine language a little bit. And here you go. Here's machine language over here. For extra credit, you can tell me what that says if you're really interested. Just kidding, there's no extra credit. But that is what it looks like, and really what we have here is hexadecimal code, not binary, which is base 12. You can tell because it has A, B, Z, C, E, F, and so forth. There's a base 16, I know. But it's more than 10 is the base. But, and we used to, when a program didn't work and it had an abnormal termination, this is in the days when I was a programmer, or it aborted, that's what we called it, abnormal termination, abort. That's where that comes from. The program would abort and we would get what we call a dump. Horrible words, huh? Which would look like this. And it showed you what the machine language looked like when the program aborted. And we used to have to go into that and translate it to figure out where the program was and so forth and so on and so on and so on. Don't have to do that anymore, but it used to be valuable to know this stuff. Not anymore, who cares? But this is what the set of instructions looks like when it runs. Here's an example of assembly language. You can see some things in here, something about pay here. Save ERT pay. Pack, this is defining data. Double precision, that's what the double is. Here's a rate. You want to list, save regular time pay, I think is probably what that is. This is a comment, and good programmers put comments in their program to document them. So this line is not executed because of this asterisk. And you can see labels out here. So somewhere in this program, you're going to see something that says, oh, here, this says go to test 2. So it's going to jump to here when that happens and so forth and so on. We don't need to go into it, but you can see very difficult to tell what's going on unless you know the language. And that's assembly, specific to each computer. What this is and what you type in as a programmer is called the source file or source program. So it's producible by humans typing on a keyboard. That's the source code, source programmer. The next step up would be what's become known as procedural languages. And the programmer writes instructions in near English, it's called, or English-like commands. And this is often called a third generation language. First being machine instructions, people used to write code in that. An assembler was one step up from, can you imagine writing machine instructions directly? But people did it. And then third generation were these. And they're a little closer to English. Here's an example. Now, although everywhere there's an asterisk, here's a comment, and the good programmers, again, comment their programs, so the next programmer can tell what's going on. And that's one of the things that differentiates experienced technologists from others. They don't think they have to document things or label files or what's going on because they assume everybody will know or the file will always be here, so who cares what the name is. But the truth is that things change, and you need to document as much as you can. But here's a statement in this language. This happens to be COBOL. Not this one, I'm sorry. That's a comment. Multiply, that's actually a word in COBOL. Wow. I can understand that. Now, regular time hours, well, the programmer created that name. It's a good programmer. They used a name you would know. Some people would just use field 1 because the programmer knows what field 1 is. Every time I see field 1, I know that's regular time hours, so why should I name it? Because the next person needs to know. Multiply that by the hourly pay rate, giving regular time pay. Okay, you can read that kind of English-like. That's COBOL. Of course, this is a decision structure. If the overtime hours are greater than 0, then we're going to compute the overtime. Otherwise, we're going to set the overtime to 0, else, if else. Typical decision structure. Here's an add. What does this do? It computes the gross pay. You're adding regular and overtime. And so forth. So that's a program some of us could understand. The skill comes in how you structure that, of course, and how you can you break the code into sections so other people can change it easily. There's a real skill to this. In art, some people would say, oh, let me back up a second. Here's the process. I type this source program in. That's what this is. This is the source. And a program, which came first, the program or the compiler, I don't know. This is a program somebody wrote called a compiler. There's actually a few more steps, but for the purposes of this class, this is all there are. The source program goes into the compiler. It reads this, ignores the comments, and tries to process the other. Where it finds verbs like multiply, it creates the machine instructions. I'll just abbreviate that MI. So the compiler's job is to convert the Near English into the digital world of the computer, the machine instructions which the machine recognizes. Now this simple statement, multiply regular time hours, etc., could be 87 machine instructions because you have to move this to the register and move this one to this other register, combine these. There's just a ton of stuff that has to happen at the machine instruction level. But you just need to tell it what to do. The compiler is what figures out how to tell the machine how to do it. The advantage of this, of course, is once that happens, you have a file created called the object, or in terms of this class, the executable, or the program file. That's what you execute. And then you also get a listing of the program as it's compiling, because if the program doesn't compile, then you don't have a program to run. And you can have errors, and it will list the errors here and help you figure out how to fix them. Or if there's no errors, at least you get a listing so you can see a printout if you need to figure out how to change the program. When you run the program, of course, you have input, have output. And this is the process, IPO. Okay, take the source. Compiler tries to recognize it, translates it to machine instruction. Now you can run the program. How big do you think Windows is? It's a program. How long do you think it takes to compile that? Well, we're not going to go into it, but Windows is a group of programs that acts like one program, really. So there's different sections of it. Real quick, since we're talking about this, the errors you can get when you're writing programs. There's two kinds. There's syntax errors. Those are very easy to figure out because the compiler tells you, it spits out the program, says, I don't know what this is. I don't recognize this. Okay? Now, with languages, some languages like C, you forget the punctuation. Semicolon's gone. Doesn't know where the sentence ends then. So there's things like that, or you misspell multiply. You say, you type it in that way. And the compiler is going to say, I have no idea what that is. It's not something you defined as a variable like pay. It's not a verb I recognize. So it spits it out. It says on line 27, I don't recognize this. That's a syntax error. Very easy to locate those and fix. The other is a logic error, which means there's no syntax errors. Your program compiled. You have an executable file. Are you done? Not by a long shot. Now you have to use test data, test your program, and see if it runs properly. And this doesn't mean you just do the Daffy Duck approach, blip, 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 you know, run it once, fix that error, run it again, fix it. No. You have some specific sets of data you run through, and you have expected results. And if you don't get those expected results, you have to figure out why. In other words, you run the payroll program, and somebody gets a weekly paycheck like this. This is the person that works part-time raking leaves, and they get a paycheck like that. I think there's a logic error. The compiler doesn't know what you meant to do. You have to figure that one out. So that means you did something wrong in your program. The compiler, of course, is stupid, like everything on the computer is dumb as a brick. Just compiles the program and you run it and you get errors because you didn't write the program quite right or you mistyped something. So that's a skill. Figuring out logic errors is more difficult than syntax because that falls on you. You've got to figure out, why did the gardener get a check for almost $1.6 million for 1 week? That doesn't seem right. So now I need to go into the program, look at the specs, figure out what happened. And of course, syntax errors happen here, and logic errors happen here. You can't have logic errors if you have syntax errors. You can't have logic errors if there's syntax errors. All right. Real quick, an interpreter is essentially a compiler that compiles a program one line at a time interactively. So you run the program and you get the results on the screen. Originally, PCs, computers came with something called BASIC, and I don't remember, that's an acronym, don't remember, sorry. It was a language, and you had to write basic programs to get anything done on the computer. So it just came up with this basic interpreter. So you could keep files of your basic program and just type in there, run this file, and it would run that program. So people started writing programs in BASIC so that they wouldn't have to reinvent the wheel every time they turned on their computer. There was no operating system at all, none. So then people started writing programs in BASIC that you could buy so you could use your computer a little more than you did in the past. In fact, Bill Gates and his buddies were playing Dungeons and Dragons. And I think I've told you this before, but one more time, so maybe it'll make sense here. So they wrote a program in BASIC, Dungeons and Dragons, I don't know how you abbreviate that, Dragons, which would pull in all their data from their last game and run it and start the game where they were before or keep track. They'd make moves. So they wrote a program that would set up their system to run their game for them. Eventually that became known as an operating system called DOS, Disk Operating System, which Bill then took when his buddies left, and he took the initial game or program, which accessed files and allowed you to do stuff and tell it which files and so forth. He turned that into an operating system called DOS, which was written in this language BASIC, which is a horribly inefficient language. And for years, Microsoft eventually converted this. This was a line-based. We've talked about that when we talked about operating systems. Eventually, they wrote Windows. Well, the first version of Windows were written in BASIC. horribly inefficient language. And it was a real problem. And finally, I don't remember, I think it's Windows 3.0, they rewrote it in another language called C. But an interpreter is what BASIC originally was. It would run programs while you watched. And it's a great way to debug your programs. Debug, by the way, those of you that wrote a paper on Admiral Grace Hopper know that she invented COBOL for the Navy, common business-oriented language, COBOL. She developed it. The Navy asked her to do it. They assigned the project to her. She developed it. Not the first language by a long shot, but it's the first language widely used by business. And she designed it from the ground up, and all languages are designed with a specific purpose. COBOL was designed to do business stuff. So you can't do very precise math with COBOL. You don't need to. You're just doing payroll. You're just doing accounting. But it's very easy to write that kind of code with COBOL. And those of you that wrote the paper on Grace Hopper will know, and you can go to the Navy Museum in Annapolis, I think it is now, and she kept a log book when they were developing COBOL. And in there's a moth taped in there with Scotch tape. And she, well, what actually happened is, I believe the story goes like this. She had some bigwigs coming in and the computer was shorting out. They couldn't figure out why. They thought it was their program. They didn't know, so that somebody opened the back and there was a moth in there shorting out a couple of the circuits, removed the moth just in time as the bigwigs came in the door so they could demonstrate the COBOL. And she kept that moth and put it in the logbook. Now we call fixing computer programs debugging. Moving the bugs, removing the moth. That's the process of fixing your syntax and logic errors. It's debugging. That's just a term. This is COBOL. We went over the COBOL, this program earlier. Just an example. All right. Here's an example of the language C. It was actually developed, I think by General Electric, I believe. I could be wrong. To run on the Unix operating system, which is a free operating system available to anybody. Although there's a company that thinks they own it now. But very efficient. Designed to talk to the hardware. Makes it very efficient to write code with, code being programs. And you can see here, it's not quite as English-like as COBOL, but you can still kind of tell what's going on. This is a comment, that /star. Here's the if, else, and so forth. You can see what's going on there. It's the same code as in the COBOL, just written in C. So a C program needs a different compiler from a COBOL program. Obviously, because it's a different language. It's looking for different words, different syntax. This is what ends a C statement, a semicolon. A period ends a COBOL statement. A COBOL program actually has paragraphs and sentences. They wanted it to be so English-like. So obviously, different syntax, you need a different compiler. Something else to think about, you need a different compiler for each machine. You can write one program, compile it on an IBM machine, and that compiler will create IBM machine language, so that program will execute on the IBM machine. Can you take that object or executable file and run it on the Mac? No. Mac's going to say, I don't know. So you can take that same source COBOL, move it to the Mac, run it through a Mac compiler. It'll create Mac machine instructions. Now it'll run on the Mac. So you only need to write the program once, but you do need a different compiler. So it's kind of like a different translator. Let's see what other examples we have here. Okay. This is where programming is going now. Object-oriented programming, or OOP. Terrible acronym. You know, it seems like you just want to add that S on the end. OOPS programming. But anyhow, you implement object-oriented design. And we'll go over to the whiteboard in a second and talk about this. You can reuse an object in many ways. Very easy. An object has events. These are some of the famous object-oriented languages. So let's go over here and talk about this for a second. This is based on the idea of a black box. Now, to many of us, the computer is a black box. We don't care. We do this stuff comes out. I don't care what goes on in there. Same with an automobile. Many people don't care. I put my key in, turn it, press this pedal, I go. That black box means you don't have to know what's going on in there to use it. Okay? What you need to know is turn key and engine starts. Press pedal, gas pedal. It goes, okay? So these are events and these are actions. What goes on inside that box, and it's black because we can't see into it. In fact, the car people don't want us to see what's going on in there. Leave it alone. It works. And of course you have to pay us to fix it, but that's another story. With programming, it works the same way. We can design, we know we need something to do something, and we need it to do based on these inputs, whatever they are, and we need it to do these actions, results. So the idea is we can design one object, give it different actions, and it'll do different results. Event driven. So I give it an event, I press pedal, this is what happens. Okay? Now, how you do that doesn't matter too much to us in this class. Well, let me give you an example. You can actually, if you get the special edition of The Lord of the Rings, I don't remember which one of the movies it was, but the extras on there explain how they did the battle scenes. If you look at those, it's almost all CGI, computer-generated images, CGI. Well, they used object-oriented programming to do that. They couldn't control each one of those. If you look at some of those pictures, there's just thousands and thousands of little computer-generated characters running around down there, fighting, dying, running, screaming. Well, they couldn't possibly control each one of those. So they used an object called, I don't know, let's just call it a character. And you could give it attributes such as, I don't know, orc. An attribute of orc going into this black box called character means certain things. They hate hobbits. Well, in English we'd say that. What it means is if an orc on the screen sees a hobbit, they're going to go after it very aggressively. You might have another one called aggression. How aggressive is this particular character? Scale 1 to 100, 1 to 10, however you want to rate it. What else? Weight, how big is it? How long are the arms? What armor is it wearing? What weaponry? Is it wounded? Etc. So inside this object, I'm exaggerating a little bit just to make the point, but inside this object then, you can have things like if this particular kind is near this, of course it's going to run towards it. If it's near a dragon, it might run away from it. There aren't any dragons, but if it's near a giant spider, Shelob, it's going to run from it. Whatever it is, this all takes place in this black box. Okay? So you can randomly kind of generate these, put all these little, the enemy over here. Each one of these is a different black box, different object. However, you're feeding them with different attributes, so each of them appears differently. taller, shorter arms, longer legs, fatter, thinner, some more aggressive than others. Some can shoot bows, some can only use swords. You get the idea. But you just generate the objects, give them the input, and they do stuff. You don't have to tell it, now run this way, do that. You can say that if you get near this, you get scared. If you get wounded, you run away. All those things are contained in the object. And they just generated thousands of objects and pressed the button and the battle happened, more or less. I'm sure there's parts of it they specifically did things, obviously, but for all that background stuff, they just let it go. Sometimes I'm sure it worked, and sometimes it didn't, and they had to tweak it a little bit. But the point was nobody had to change each one of these little boxes and control it. The software did it, because it was an object called character that was going to fight in this battle. You randomly generate this stuff to some extent. You got to have the right people on the right side. The right armor goes, you know. But you can do that in the object. So if you say to yourself, you know, that's too many orcs, we need more Uruk Hai. So you could add that in here instead, have more of those, and so forth. So once you have those objects in the computer, they run around and fight a battle without you controlling it. Right? That's the idea. Object-oriented programming is what they used. And they discuss it on one of the extras of the DVD if you want to watch it. In real life, so to speak, what you can do is invent an object that prints. In C, this is what you get. They're called libraries. And all you need to do is point the black box called print to the right input that you want to print, tell it where to print it, how to print it, and it does all that for you. So you don't have to rewrite that object called print. The C doesn't have that many commands. What it has is libraries of commands that other people have written. So you don't have to reinvent the wheel. It's done for you. This is a much higher level thing. But you might also have a box called compute salaried payroll. Well, you don't want everybody to know how salary is computed. So you have certain programmers you trust. They write that black box. And you tell the other programmers, this is what I need to come in, and this is what you get out. No one else knows what goes on in there, but we can still run our payroll. That's another use of object-oriented. So we're getting the same kind of approach to databases, where we have objects in databases. It's a very important concept, and it's going to become more so. Probably won't affect many of you people directly. However, when you hear the term now, you'll have some idea. And if you get a chance, watch that DVD. That'll give you some idea too. This is a very important language, Java. Got the name because these people were tired and it was late, just like you'd think, and they were drinking lots of coffee. At Sun Microsystems, and it's free. They don't charge for this, but everybody has it on their computer. Because Java was designed to work on the internet. Here's some Java code. It's not as English as COBOL, is it? It's not intended to be. This is a very efficient language, so it doesn't have a lot of obviousness to it. These are locations. This is defining a data type, integer. Here's a computation. Inches divided by 39.36 equals meters. That's how many inches in a meter. But you can see some of this, but you notice there's a brace. Brace, that's one statement between braces, just to give you some idea. This is an object written outside this program. So this object, g.drawImage, has these attributes going into it, one called logo, which we define up here. And this is probably size, dimension, and so forth. So that object is going to draw something based on what we feed it here. And this is what it's drawing right here. So this program created this. All right? It uses just-in-time compiler. That's similar to an interpreter. But this is what gives Java. We used to call this the JVM, I don't know when it changed, Java Virtual Machine. This is what makes Java so powerful and so useful on the internet. We have our web server, and the Java exists on the web server, your applet they're often called. On the last screen that was an applet that drew that sun. We have my computer at home. I go to a web page. This Java applet comes across onto my hard disk and runs from there. Well, one of the problems with the web is, of course, they have no idea what hardware and operating system I'm using. So we have this thing called the JVM, Java Virtual Machine. The Java goes in here. This is specific to my hardware and operating system. So the applet runs from inside here. This, they call it a virtual machine because it's creating an environment like the machine it needs to run in. So the very same Java runs in this JVM on my system. There's a different one for your system, a different one for the Mac. Same Java runs on any computer on the web, as long as you have that JVM. Similar to a compiler, it just happens in real time. That's all. So it executes that Java incredibly fast because it's so efficient. And it actually moves it to your computer and runs it. That's a good thing too, because the connection speed, or the bandwidth, only is concerned with moving that tiny little bit of Java over here. Then it runs off here. And if it needs to run more than once, it just runs it off here instead of going all the way back here. Makes Java very valuable on the web. It was designed specifically to do that, and they did a great job. And here's the applet, which is moved down to your computer, runs on your JVM, and makes the web more interesting. A couple other things. C++ was just an improvement on C, and it actually, C wasn't specifically object-oriented. Purists say it isn't, but it is. Depends on who you talk to. C++ makes you use object-oriented coding. So it's an advantage. But the other thing, PDE, programming development environment, C++ was kind of, there's a lot of them, and there were some before then, but C++ developed a software interface in which you could develop your code, and it took care of a lot of the tedious stuff, like it checked your spelling. It made the verbs in a certain color, comments in other colors, so it color-coded stuff. And you could run the program right inside that environment, and it would tell you what the results were, what the errors were, make suggestions. So you wouldn't compile it till you got rid of all the errors and tests. Then you would say, I think I'm ready to try it, compile. Then you would compile it. Now everything uses that kind of approach. There's Java environments. By the way, Java can also be compiled. It doesn't have to run like we just talked about. It can run in both ways. C# is just another version. Designed more for web apps. That's all I'm going to say about that. You know, not going to go into this stuff. Visual Studio is just a development environment where you don't have to write the code. And this is an example. They all do similar things. Visual Studio is the one Microsoft put out, and it has Visual Basic, ++ and Sharp all combined. You can use any of the code, but it just has interfaces. I want a box. Here's the label. I want it to be this big with these lines. Boom, and it creates the Visual Basic, C++ or C# code for you. You don't have to do it. That's what we're talking about here. Some would call this a 4th generation language, as are these. The idea here, of course, is no longer do you have to type box this size. You just tell it. It pops up. There's an object. You tell it, I want the box this big, located here, this color, boom, done. All right? And you can do all kinds of things. They're calling this a visual programming environment. Okay. Same thing as what I was talking about, programming development environment. And we don't need to talk about those. Back here a second. This is one of the early languages too. RPG, it's the first language I learned after BASIC. Report program generator. Very odd language, not used too much these days, but believe it or not, IBM developed some hardware where the code for RPG-3, they called it, was actually embedded right in the hardware. Incredibly fast. So RPG survived a little longer than it should. It's still around, but it's not I mean, this C tells it it's a calculation. It has to be in a specific column. Not only you have to use the C, it's got to be in the right column, or the compiler doesn't like it. Very odd language. This is the language we talked about with the database assignment. SQL, structured query language. And here's the language here. So instead of all that stuff, with the old languages, you had to define the input. Here's where I'm getting the input. Here's what the input looks like. Here's what I want to do to the input. Find the output. Please put the output there based on the, etc. Well, SQL avoids all that because it has to work with a database, DBMS, as we talked about, where this name's already defined. Select is a verb, recognized by the SQL interpreter. That means get these, of course. These are field names you define in your database. So I want those 3 field names from another verb. This is a table, these are fields. And those fields are in this table or file. Should be familiar to you. Where means this is the conditions. Show me these fields in this table only when the overtime is greater than 0. And you can also tell it, sort it by last name in alphabetic order. Very powerful, powerful language. And the beauty, besides being powerful and simple, this is understood by any relational database. That's a specific type of database, relation, as we talked about. So if you learn this, any database you use these days, pretty much, very few other than relational these days, it's going to know what you're asking for here. All right, and here's the results down here. Sorted by last name. A lot of people argue this is not a program. This is not a programming language. I used to think that way, and now I don't care. It's very similar. It's just very powerful. So this would be called a 4th generation language because so much of what goes on is because of the database, not the program. Very simple for you. Here's a list of some languages. Basic we talked about. Ada, those of you that wrote about Ada Lovelace, this was named after her for your word assignment. And of course she was Lord Byron's daughter, and her mother didn't want her to be like him. He was a poet. So she encouraged her to go into mathematics and engineering, and she developed first programmer in history. The military designed this language called Ada to do parallel. You can write a program where more than one thing happens at once. Most programs, it's like a pachinko machine. There's one thread going through. That's a bad example because there's all kinds of little balls going through a pachinko. Anyhow, there's one thread in most programs. With an Ada language, you can do parallel processing. You can have many things happening at once, and then they all come together at the bottom. Different kind of programming, you got to have skill in it. They wrote it so that on a tank that has more than one gun could do, one program could do firing, acquisition and firing for more than one gun at a time because they didn't want to wait. And it works very well, still around. Let's see. Fortran was one of the first languages developed. It's for engineering. probably still around because it's very accurate. First language I took in college here at New Mexico Tech was Fortran. Don't tell anybody, but I got a D in that class. Didn't do so well. I got better at programming later on. It was all about motivation. You can understand that. Lisp is a list processing language. Lisp. It's very odd because all you do is feed it lists of things, and the language then finds patterns in the lists. It's an artificial intelligence language is what it's intended for, and the bigger database you give it, the more output it has. It kind of tries an answer, and if that's not right, it tries a different one until it gets it right. I'm just talking about some of these. This is also an artificial intelligence language. Tries to make sense out of patterns. Pascal was developed by a guy named Nicholas Wirth, and he donated it to the world. And he never intended it to be used for anything. It was specifically designed to teach object-oriented programming. I used to teach it for the University of Maryland. It's not in vogue anymore. We don't use it. We use something like C or Java now to teach programming. But it was designed because it was simple and it forced you to use objects. When I was teaching for Maryland Europe, I found out that, shockingly enough, the flight control system for the Brussels airport was written in Pascal. I was shocked, but I guess whatever works. And that's just a list of languages. And we talked about this earlier. This is an application generator. This allows you just to enter stuff about what you want to do, and then the source code is created for you. One of the drawbacks of those applications generators is that the code that's generated usually isn't very efficient, but that used to be an issue when we had to worry about how slow processors were, how much RAM we had. And so application generators didn't, although we're around, we tried to discourage them because the code was so inefficient that it would just bring the system to a halt. Now we don't have to worry so much about it, so we can give those to people and they don't have to worry about all those little things that you have to worry about when you write source code. Let the system do it for you. This HTML hypertext markup language, we'll talk about this more later when we talk about developing a web page, but for now, this is the language your browser understands. Your browser's Internet Explorer, Mozilla, Safari, whatever you use on your computer. These are HTML commands. Notice it starts with HTML. A head is a certain type, and every HTML command starts and ends with that. And the last part of this head command here is here. So you start with head, you end with slash head. Everything in between is part of that header. So you can see here, convenient takeaway meals for all occasions. And if we could see this website, that would be shown some. I'm sorry. This is metadata. This is what Google uses to do searches. So they put this in here for the search engines. That's what metadata is for. Let's find something we can see here. Well, it's hard to see here. Let's do a little experiment here. We'll do that later. But if you go to this website or any website, click on View at the top in your browser, Source, it'll show you the HTML, believe it or not. I think I mentioned this earlier, but try that. Any website you go to, it'll show you the HTML because nobody bothers to hide it. HTML was intended to be an open source kind of thing, which means anybody should have access and be able to use it. You can't change their website. You couldn't change the HTML and put it back, but you can look at it. And go to any website, click on View Source, and you'll see the HTML that made that website. Script languages work with web pages as well. This one is just huge these days. Stands for pre-processing hypertext processor. So this happens on the server, unlike what I talked about earlier where it happens on your computer. But this allows a database full of commands to be used on a web page. I'm not going to say any more than that. JavaScript has nothing to do with Java, by the way. It's just the name they chose to latch on to the popularity of Java. But it's used in a lot of websites to execute very complicated commands. And I'm not going to go into this. This is just a different version of HTML. The guy that Bernard-Lee, the guy that invented HTML hates this kind of thing. He thinks it should be kept simple and straight. That's its strength. But people have made all these extra things that allow it to do more. Extensible markup language. We're not going to go into this stuff, but it's just different ways to do web pages that make it more flexible and more powerful. Ajax is around. A lot of people use it. Love this name, Ruby on Rails. Next time you're in Borders or somewhere, go over to the technical part and you'll see books on Ruby on Rails. Dreamweaver, that's part of Microsoft's Office if you get certain versions of it. And that allows you to type open text and it creates the HTML, much like the application generators we talked about earlier. Well, similar kind of thing. You just type open text, you format it like you would in Word or something, and it creates the HTML, hypertext markup language, to work with a web page. So it generates the web page for you. One of many tools. Multimedia authoring software, just another version of software that allows you to pull stuff together, make it work as a whole without having to write a lot of programs. And that's where we're getting to these days. There's programmers writing the underlying code for all these tools. We're getting fewer and fewer programmers writing actual programs. It's hard to read this, so just see if we can talk about it a little bit. But over here is the SDLC, System Development Lifecycle, we talked about last time. Here's the step 4, implementation. And of course, that is the programming, or part of that is the programming. And this is the program development lifecycle, or cycle. And the steps are analyze requirements, design, I just drew a blank. I can't read that. Sorry. I'll have to see if I can get a better version of this. But the idea is then you implement it, the design, or you validate the design, implement the design, test it. Then you document it. So it's a similar approach. Analyze, design, validate, and that might include sitting down with other programmers and you go through the logic you've designed before you actually write the code, just to get some feedback and a reality check. And then you actually write the code, test it, and document it. Of course, you should be documenting it all along. And then, of course, it goes on because you might find errors and so forth. That's classically what programmers do. I don't know how many of them do it anymore, but that's what we're talking about. Couple more things, and then you'll be done with programming. Many of you probably are bored to death. You're wondering why we're even talking about it, but it's very important. In that, I think you should understand a little bit about programs. You might want to do a web page. You might have a discussion with a programmer. You might be on a team doing some kind of development. And if you have a little bit of understanding, you'll have a better input into what's going on. And this is a familiarization class, fundamentals of technology. So this is a fundamental. A sequence control structure means how do programs run? Most of them go one line of code, do it. Next line of code, next line of, that's what a program does. 1, 2, 3, 4, 5, 6. Ada is an exception. It can run 1, 1, 1, 2, 2, 2, and so forth, but most programs for the purpose of this class run right down the list of instructions. You do 1, you do 2, you do 3. That's called the sequence control structure. We can modify that structure. This is why we introduced the structure with an if-then-else structure. This is how you diagram them when you're documenting it. You have a condition diamond. If it's true, you go here. If it's false, you go here. Only it's a binary type of thing, if else. If this is true, do this. Otherwise, or else, do this. Same thing, true, false. If this condition is true, if it's false. Then you do action 1, then you do action 2. You don't do both. So now we've just modified that sequence a little bit. We all know what if else is. Another thing you can do the same thing with if else. You just have if else, if else, if else, if else. This is a type of code called a case that makes it much simpler to do this kind of thing. You just say, here's the conditions. When these conditions are true, do this, 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 or this, or this, or this. Not a big deal, just giving you a little insight here. Last thing is repetition. Control structure. You might hear that called a loop by programmers. Two basic kinds work exactly the same way except for when the condition is tested. Do while says test the condition before we go in here. If the condition's true, then we do the action. If it's false, we're done with the loop. We go somewhere else. We go to the next statement under here is where we go. So if it's false, we make the next statement under here. Otherwise, we continue in this loop. We do this, go back up here, test again. The other one is do until. The only difference is it's tested after the action. That's a loop. So you might think about it this way. Microsoft Word runs while you have not pressed the exit button or the X. So that's a while loop. It's going to run until you do that and continue to run until you exit. Think about it like that. Or run until you've got to the end of file. Read a record, process a record, print a check. Are we at end? While we're not at end of file. That's a loop you'll see often in programs. You have to write that into your code. Read this file until it's at end of file. End of file comes from the file. The operating system sends you a flag that says end of file. Then the loop quits. And I think we're just about done. You can watch this video. It's about discussing with EA, Electronic Arts, a guy is talking about modifying games to run on mobile phones. All right. So we've looked at languages, web development, and the programming development cycle. I didn't make this too long, I hope, for you. But I think it's interesting to see what code looks like, to have some understanding of how we generate instruction file for the computer. If you ever talk to a programmer, you'll have a better understanding of what they're doing. Later on in class, we're going to ask you to create a web page, a simple one, using HTML. And some people argue that's not really a programming language, but I don't argue about it anymore. I used to feel that way, but it is a language and it creates an output. So we'll be talking about that. So I hope you got something out of talking about programming, and that's all for tonight. I'd like to give you an assignment, which is to talk about the SDLC a little bit. If you were at a school and somebody needed to develop a system to do registration because everything happened manually, how would you convince them to use SDLC? Why would you want to do that? It seems like a lot of work to some people. How would you convince them? Even if you don't feel like it's the way to go, based on what we talked about last time. And, you know, you can think about the programming aspect of it too. Why does it make sense to do things in phases like that SDLC? And just make it a 1 or 2 page paper. Do research if you want, but mainly just put your own words in there in a document to convince somebody to use SDLC. Why do you think it works? And why is it going to save money? Is it going to save time? Is it going to make a better product? All those things. And you're convincing somebody that's your superior to use it rather than just start programming like your boss always wants to do. How hard can it be? It's just a program. Well, how do you answer that question? All right. Thanks. I'll see you later.